In this video, we're going to take a look at how to calculate density, and we're going to use the same compositions we used for calculating viscosity. These data from Michael Clynne from the Chaos Crags, where we have data from the various domes A through F as examples. So in these first few columns, we have temperature and pressure, which we've just kind of made up because we're going to need those for the calculations. Then we have these so-called liquid compositions. Here I've put them in quotation marks because they're not really liquids. We know that they're mixtures of both liquids and crystals. These are very crystal-rich compositions. So we're just going to pretend that they're liquids. We could make a correction later on, accounting for the density that is added by part of the system being crystalline, but we'll just treat them as liquids for now. So those whole rock compositions are put here in columns F through P. We've got, well, actually through Q because we have water contents inserted here. Then we take those values and convert them to mole proportions. So we have molecular weights here of the oxides. Notice that we're not using cation fractions, so we have the traditional mole proportions of Al2O3 and Na2O, etc. So these are the mole proportions in columns U through AG, and then those are converted to a renormalized total where the sum is fixed to 100. I'm going to leave it as 100 here. We're going to use mole fractions in the equation. That was given to us by Lange and Carmichael 1990. So we're going to use these xi here. So that is a mole fraction, not a mole percent. But we can make that correction at the end. If you had values that were not normalized to 100, if you had 0.69 instead of 69, then you would end up with the same values, just multiply it out. Or divided out by 100. We'll see that at the end. Let's take a look at this equation here, then we'll do the first couple of calculations to get things set up. And then we'll have a second video where we'll complete the analysis. So we're going to use this equation here from Becky Lange and Ian Carmichael's paper of 1990 in the RIMG special volume, where we have the volume of the liquid. This is what we're going to calculate per mole as a function of temperature, pressure, and composition. And that volume of the liquid, if we have 1 mole of liquid, is going to be equal to the sum of all the partial molar volumes that are given here that vary as a function of both temperature and pressure here. So we have these xi, those are the mole fractions. We're going to treat them as mole percents and make the correction later of all these fellows here. So those are the xi. So if I is SiO2, then we use these coefficients here. When I is TiO2, we use these coefficients here. Let's take a look at this first entry here. That's this first entry in the equation there. This is the volume of I. Let's take a look at SiO2. If we had 1 mole and the volume is in cubic centimeters or cc, this is the case at when the temperature is 1673 kelvins, and it's not noted here, but it's also the case for the volume when it's at 1 bar. So if we have 1 mole of pure SiO2 liquid, then its volume would be 26.9 cubic centimeters. If we had 1 mole of pure TiO2 liquid, then its volume would be a little bit less, 23.16 cubic centimeters. Again, at 1673 and 1 bar. What if the temperature is not 1673? And what if the pressure is not 1 bar? Then we have these columns over here to make those kinds of corrections. The correction for silica is 0, so we can just kind of ignore that. That's not terribly interesting. What they're saying here is that in the results of their calculations, the silica liquids, a pure silica liquid would not expand very much, almost a trivial amount. Show a plus or minus 0.5, so it could be as high as plus 0.5 or as low as minus 0.5. Notice that none of these are negative, though. We wouldn't expect them to be negative. If something was negative here, that means the volume would shrink as we heat it. So the positive values mean that the thermal expansion coefficient is positive, so things expand, except for silica. But titanium will expand. By how much? Well, if we have 1 mole at 1673, it takes up 23.16 cubic centimeters of space. If we heat it up a little bit, let's say by 1 Kelvin, that is not a minus sign in that units, that should be a multiplication. Then we would heat it up, it would expand if we increase the temperature by 1 Kelvin by 7.24 times 10 to the minus 3. So don't forget to add that factor here. That means if we increase the temperature by 1 Kelvin, then the volume will increase by 0.00724 cubic centimeters. What if we compress the system? Well, you can see that most of these are negative, and that's as we would expect. If we add pressure above 1 bar, then the system should get smaller. It's interesting, a couple of values are positive here, so they would, in theory, get larger. That would probably not be the case for pure MgO or calcium liquids, but it's probably just the way these oxides interact with one another in the liquid. So most of these are negative. Here for TiO2, if we increase the pressure by 1 bar, then we would decrease the volume by minus 2.31 times 10 to the minus 4. So it's a very small correction. So 0.000226. That would be a negative value would be the change with respect to a 1 bar change in pressure. And then finally, we have this fourth column over here that we're not going to use, but we'll just look at it briefly. This dVdP, this change of volume with respect to pressure, might also in turn be a function of temperature, and they find that it is. That if we change the temperature, then the rate of change of volume with pressure is not constant. So this is the dVdP at 1673. If we have some other temperature, we can make an additional correction here. And those are the coefficients here. Notice that they are at magnitude of 10 to the minus 7. That's very, very small compared to these corrections here. And it's so small that that is probably the reason why Lange and Carmichael have left it off of this equation here. So it's not part of this equation. There's not an extra correction for dVdP as a function of temperature, but there it is in case we wanted to use it at some other point. So we're just going to use these first 3 columns, and we'll enter the first couple of coefficients. What we need to do first is add a couple of columns. We want this temperature difference relative to 1673. So we'll write temperature minus 1673. Now this has to be in kelvins. So over here, we'll take this arbitrary temperature, we'll add 273.15 to convert it to kelvins, and then we'll subtract 1673. So we have the difference in temperature relative to 1673. That's the temperature that we say the system is at. We're assuming that it's at 1,000 degrees centigrade or 1273 kelvins, and it's about 400 degrees below the reference temperature of 1673. So that's that difference that we'll be using. And then we have to look at the difference in pressure here. So we'll have pressure minus, not plus, minus 1 bar. And we have some arbitrary pressures over here. We have 2 kilobars. So we'll take that, multiply it by 1,000 to convert it to bars, and then we will subtract 1 bar from that. So we have a system that is 1,999 bars above the reference of 1 bar. And we're going to make use of that. We're going to do calculations for all of these oxides, including water. We're going to use another paper by Lange, Feldstein and Lange. We'll look at that later. So for the silica correction, let's look at how that would work. So for the case of silica, we have equals x, that's x. X sub I is silica for this case. And so we'll take the mole percent, and we're going to multiply it by a sum. And the sum that we're multiplying it by, notice those square brackets. I've entered brackets to represent that first square bracket there. We have V sub I 1673, so that's 26.9. And then plus dV dt, that's this, that's 0. We don't even have to add anything else there because it's just 0, plus dV dP, which is minus 1.89 times 10 to the minus 4, and that is multiplied by the difference in pressure, P minus 1 bar, which is there. So now we're taking advantage of that column, close the parentheses, and hit return, and we get this value of 1846. And we'll do the next step for titanium. So titanium is a little more interesting because we have the non-zero value here. For titanium, that's the x sub I when I is titanium. So we'll take this value here, multiply it by, we'll have the open parentheses because we have a number of things we're going to multiply it by. The V sub I for titanium is 23.16 cubic centimeters. And then we're going to add to that the temperature correction, and that is going to be 7.24 times 10 to the minus 3, and that'll be multiplied by T minus 1673, which is this fellow here. And then we'll add to that the pressure correction, which is minus 2.31 times 10 to the minus 4, and then that'll all be multiplied by the P minus 1 bar, which is this fellow here. Close the parentheses and then hit return. So that is our correction here. So what we have, we could divide these things out by 100 to make a little more sense of them. We'll do this at the end also. So if we have 1 mole of a mixture, a liquid that is not pure silica, but a mixture of silica plus titanium plus these other oxides, then its volume is going to be the sum of all these partial molar volumes here. So pure silica would take up 26.9 cubic centimeters, but in our system here, it just takes up 18.46 centimeters, multiplied by 100 because we have these mole percents rather than mole fractions. For titanium, if we had 1 mole of titanium, pure titanium liquid, not pure titanium, but titanium oxide, TiO2, it would take up 23.16 cubic centimeters, but we just have a little bit of titanium. It is just 0.31% of the whole system, so it just takes up 0.06 cubic centimeters in this mixture. Now in the next video, what we're going to do is we're going to finish off the rest of these oxides, make a correction for water, and then complete the calculation to convert our volume calculation into one of density, which is the number that we're eventually want to calculate.